Kinematics of circular motion. I will start talking about the circular motion from the acceleration part using Newton's second law. Net force equal to rate of change of momentum. If mass is constant, then net force becomes mass into acceleration. So if we know the acceleration, we will be able to understand the cause of motion. So starting from acceleration itself, I want to talk about the type of accelerations a particle doing circular motion may have. As acceleration is basically rate of change of velocity. Velocity is a vector quantity either by changing its magnitude of instantaneous velocity, or it may change in direction of velocity, or maybe in both. I just want to clear it into two separate parts. In one part, I will talk about changing velocity due to change in its magnitude, while in the next part I will discuss about the change in direction of velocity so as to get clear information about the circular motion. Remember, if acceleration is due to change in magnitude of velocity, then it is termed as tangential acceleration. Particularly in case of circular motion, it is tangential acceleration. While on the other hand, if acceleration is due to change in direction of velocity, then it is taken as radial acceleration because its direction is always along the radial direction. So to explain these further, I will use tangential acceleration to be AT and radial accelerations by symbol AR. If we combine both the two accelerations for a particular particle, then net acceleration of the particle can be taken as under root of square of tangential acceleration plus square of radial acceleration. This is the net acceleration of any particle which that may have. If particle is revolving in this circle, then at the instant when it reaches at this point, it has two independent accelerations. One is along the radial direction towards the center. It always remains center seeking. That's why sometimes we also call it centripetal acceleration. As radial acceleration AR is always center seeking, that's why sometimes we also call it centripetal acceleration. Now I want to show you how to get these two accelerations from the data given about a particle moving around a circle. So just see, first of all, we are going to talk about time rate of speed. Its direction always tangential to path. For example, if speed of particle is alpha t square plus beta t, then at is equal to dv by dt, which becomes equal to twice alpha t plus beta. So here this is the result for the tangential acceleration of the particle moving with velocity alpha t square plus beta t. We easily get this result from this relation. Now, some facts are worth noting. Some points about the radial acceleration are noteworthy. So, remember these points. The first point is it is due to change in direction of motion. We can also say vice versa to it, means it is the radial acceleration which changes direction of motion for the particle. How to get its magnitude? It is just a very easy task. Let us consider a particle is revolving in this circular path about this center C. At any instant, say particle is in this position, and at some other time, a little time apart. If we talk about the particle, it was in this position, say A. After passage of some time, it reaches somewhere at this point B. If tangential velocity at its initial position A is considered, then it will in this direction having magnitude V. We can call it V initial. After some time, a very little time, say its velocity's magnitude is still same, but if we talk about the direction of motion, then it will be somewhere in this direction. Again tangential to its path. If we talk about the change in direction, then it can be measured in terms of this angle, say theta. If this angle is theta, then obviously this angle will also be theta, because these two tangential lines are perpendicular to line CA and CB, so the angle between CA and CB will be same as angle between normals to these two lines. So this is theta, this is also theta. Our main aim is to find change in velocity per unit time. So if I start calculating, then obviously change in velocity can be written as delta V equal to V final minus V initial. It can be easily taken as V final is somewhere in this direction and V initial is directed somewhere in this direction. This is center C. Now, as we have to subtract this V initial, I am taking V final in this direction, and as I have to subtract this V initial from V final, so as there is no separate procedure in vector analysis for the subtraction, we just follow the addition of negative of initial velocity vector into the final velocity vector, then obviously V final minus V initial. So just see, I have just inverted the initial velocity vector to form it as V initial, negative of V initial. As we know, this is vector and this is also vector. So if I add these two vectors Vf and negative of V initial, then by the vector addition, as V final and V initial have the same magnitude, so we can say that change in velocity have the magnitude equal to 2V sine theta by 2, which may be obtained by putting V in place of Vi and Vf, and solving this equation directly leads us to 2V sine theta by 2. Now, time taken to travel given theta angle is t, then radial acceleration AR can be written as magnitude of change in velocity divided by the time t, which can be further written as 2v sine theta by 2 divided by t. This t can be written as theta into radius, the arc length, and speed is, tangential speed is v. Then this time taken t in travelling theta angle can be written as theta r divided by v. So now we get AR equal to twice v sine theta by 2 divided by theta r divided by v, or AR is equal to v square by r into sine theta by 2 divided by theta by 2. So for small angles, this sine theta by 2 divided by theta by 2 can be written as unity. So AR is equal to v square by r. This is the final result. For this radial acceleration, we had seen on the previous page that its direction is along the radius. That's why, because it is directed towards center, it is called centripetal acceleration also.